So I'm going to talk about something quite different. I'm going to talk about something called private data aggregation. It's something we've been working on for a couple of years now, and I just wanted to kind of give you an update of some of the new things that we've recently published in this area. So private data aggregation is probably a problem that affects many of you. So the problem is basically, can we kind of learn aggregate information about a large user population without learning anything else about the underlying user data? Okay, that's kind of the problem we'd like to do. And this comes up in many different contexts. For example, these days when products sort of roll off the factory, when a car rolls off the factory line and it's delivered to the customer, in the past, the manufacturer would never hear back from the car. But these days, cars are connected and they constantly send reports back to the manufacturer. Similarly, browsers like Firefox, they want to be able to understand how people use the browser so they can make the browser better, right? So, if you deploy a new feature in your product, you probably want to know, do people actually use it or do they ignore it? How did they use it? And those kind of questions will help you basically improve your product. So today, actually, I should give a few more examples. Like maybe a browser is also interested in questions of the type like, what are the most common websites that people visit these days? Or what are the most common websites that people set their home pages to? So the goal is to learn sort of the most common websites, but learn nothing else about the user population. And even simple questions like, how many people are currently on the Golden Gate Bridge? Right? We all know individually if we're on the Golden Gate Bridge, but we'd like to sort of collect this aggregate information without learning actually who is on the Golden Gate Bridge, right? We want to know how many people, but not who. So the way naively you would think of building a system like this is basically you would just have the product report everything back to home base, and then the home base would aggregate the information. And that's actually really problematic because it's very privacy invasive, right? I mean, you're reporting a lot of information back to the manufacturer. The manufacturer doesn't care about who is on the Golden Gate Bridge. They just want to know how many people are on it, yeah? And so the question is, can we do anything better? All right, so this is kind of the paradigm of privately aggregating data. The goal is just to get the aggregate data from a large population, think millions or billions of users, but without learning anything else about their individual data. Okay, so that's kind of the goal. So now let's dive in and see sort of the high-level paradigm of how we do it, and then I want to tell you about some new results. So the high-level paradigm, again, these systems are supposed to aggregate across billions of people, so they're supposed to be extremely efficient and scalable, yeah? And so it turns out the most efficient way we know how to do this is by using the server that wants to learn the information. I'll use Mozilla now because they're actually using one of these systems that we designed. But then it turns out there's also a need for a helper party. Yeah, so a second party that's non-colluding with Mozilla, and I'll explain what the helper party is in just a second, what it's needed for. Now, the way the system is going to work is as follows. Basically, every user has some data that they want that is going to become part of the aggregate. What they're going to do is they're going to use simple secret sharing between the server and the helper, right? So literally, you take your data, you split it up into two shares, such that the sum of the two shares, there's a left share and a right share. The sum of the two shares happens to be your actual data that you want to contribute, and you send one share to one party and the other share to the other party. You notice that the helper is just getting random noise here. He's not getting anything useful. Similarly, the server is also getting just random noise. So individually, neither one of these knows the data in the clear. Of course, if they collude, they can recover the data in the clear, but the assumption is that these are non-colluding parties, and again, we'll talk about the assumption in just a second. So basically, all the users in the system are going to do this. So everybody splits their data, sends it to the server and to the helper, and that's kind of how the system operates. Now, what is the purpose of this helper? The only thing the helper is there to do is basically sort of audit the server. Yeah, so to make sure the helper is there just to make sure the server doesn't learn things it's not supposed to learn. The helper itself doesn't learn anything in this process. It's just there to prevent the server from learning the data in the clear. The server will only learn the aggregate. Okay, so that's kind of the basic mechanism of sending data back to the manufacturer. By the way, I should say in the real world, this helper service is actually implemented by something called the ISRG. That's one example of a helper service. So there are these helper servers that are already available for people to use. Okay, so now when we kind of go to the next step, so now we have our server who has shares from a billion users. We have the helper who has shares from a billion users. And now what do they do with these shares? So now what they'll do is basically they're going to do some sort of a very lightweight computation between the two of them, right? So they have a huge amount of data shared between them. Neither one of them knows any of the data in the clear. They're going to do some sort of a shared computation between the server and the helper, and the result is going to give you basically the result of the analysis. Okay, so whatever it is you want to learn, right? How many people are on the Golden Gate Bridge, how many people use a particular feature, and so on. So that's kind of the high-level idea. Now, I want to give you some specific examples of things that we can do very efficiently today, and then we'll jump into a particular example. Okay, so let me give you 3 examples. So the first example, that's kind of the most obvious one, is what if we would just want to compute a sum over a subset of the data elements? Yeah? Maybe we want to compute a sum over, like again, of how many people are on the Golden Gate Bridge. You know, everybody would contribute either 0 or 1, depending whether they're on the bridge or not. And we want to compute a sum over, say, the entire population. So the way this works is basically the server sends over the set that it wants to compute the sum over. Yes, the helper basically would compute the sum of its shares, of the shares in the set where we're trying to compute the sum over. Potentially, the helper would also add some noise, but we can ignore the noise for now. And then the server would add its own shares to the sum, and you can see that basically by computing the sum of sums, we get the final sum, potentially with some noise that's added to the result. Okay, so the server basically learns the result of the sum, again, potentially with what's called the differential privacy noise. Does that make sense? So the helper computes a subset sum, sends it to the server adds its own subset sum, the two sums sum up to the actual sum, and so the server learns the result, but the server doesn't learn anything else. Okay, so this already lets you learn, this very simple idea already lets you learn about, for example, how many people use a particular feature in your product, right? Maybe you shipped a new feature, you want to know how useful it is. Already this lets you do it. It's used, for example, in exposure notification applications where you want to know how many people were exposed without actually learning who was exposed. Yeah, so that's a way to learn all that. There are a lot of challenges here in that the server actually, clients could actually try to disrupt this computation. So the server needs to drop invalid contributions. I'll just tell you that this is all handled in a system called Prio that we designed a while ago. I wanted to also give a shout out to something called Prio Plus, which actually saves a bit of communication in the system at the expense of more work between the server and the helper. So there's actually, this is the Prio system that what it does, and there's actually quite a lot of work about that, but that's not what I wanted to talk about. So this is the first example, computing sums. The second example, which is actually what I wanted to talk about more in more detail, is computing what are called heavy hitters. Okay, so again, we have our two sets, right? So we have our server who has shares of the data, and the helper has shares of the data. And together, what they want to do is find out all the data items that appear at least t times in the entire corpus. Okay, so for example, maybe you want to learn what are the most popular home pages. So you want to learn all the home pages that appear more than t times and learn nothing else about the data set. Okay, so that's what this would do. We call this heavy hitters. So we have this shared data between a server and a helper, and we want to compute all the heavy hitters in this data set. So the way this is going to work is, again, we're going to do some lightweight protocol between the server and the helper. Again, lightweight because, again, this has to scale to billions of users, and the result is going to be the set of heavy hitters, and the number of times that these heavy hitters appear, and nothing else will be revealed to the server. Yeah, so again, this is a problem that probably many of you are seeing in practice, in that, again, within the user population, you want to know what are the most common patterns that the users are experiencing. You want to learn about the heavy hitters, but you want to learn nothing about the long tail, right? The long tail usually contains a lot of sensitive information, and you want to learn nothing about that. Okay, so I'm going to show you a protocol for doing this in just a second. So this is something that we published earlier this year. Does that make sense? Everybody with me so far? Okay, great, thanks. And the third example I'll mention is what we call a shuffle. Again, so we have shared data between the helper and the server, and what we'd like to do is basically output the server should learn all the data items, but in a randomly permuted order. So the server wouldn't learn which data item belongs to who. Okay, so this is called a shuffle. So it learns, again, the set of data items, it randomly permuted. And why would you want to do that? Well, it turns out that's actually pretty useful for computing histograms. So, for example, if you want to compute a histogram of the data that you have, how many times did each data item appear, then you can shuffle everything. Now once the shuffle becomes public, you have no idea which data came from who, and now you can build a histogram of the actual data without revealing who did what. All right, so that's another way to compute it. This is actually recent work that I did with one of my former students, Saba Iskandarian, building on some earlier work. Okay, so those are 3 simple examples of what you can do once you have shared data. All right, so what I wanted to do is give you a few examples of how these things work. So let's dive into the private heavy hitters system. Yeah, so let me show you how to compute private heavy hitters. It's kind of a cute system. So again, the goal is to learn data that appears at least t times, but learn nothing else. Turns out there's a star here because in the most efficient protocol, there's a little bit more information that's leaked, but we'll ignore that. Okay, so how does this work? So here's, so again, remember our goal is to learn private heavy hitters. So here's what we do. So every client is basically going to prepare a binary tree. Now, but what is in this binary tree? The number of leaves in this binary tree is actually the total number of URLs in the entire world. Actually, you can think of it, if a URL is a 32-byte string, you can think of the leaves of this tree as all 32-byte strings. So that's an enormous number of leaves, right? That's an exponential number of leaves, but let's not worry about the size of the tree for just a minute. We'll compress it later. So we have a tree where all possible URLs are leaves of this tree, and then the user wants to share a particular URL, which is, say, the user's homepage. So what they'll do is they'll find the leaf in this tree that corresponds to their homepage, and basically they'll set the path to that leaf to be all ones. All right? So that's kind of the tree that the user is going to prepare for the data item that the user is going to contribute. Now the user, what it will do is it will randomly prepare 2 random trees that basically sum up to the original tree. Okay? So you can see the top tree is a random tree, the bottom tree is a random tree, but if you add up the values in all the nodes, you'll get the actual tree that represents the user's homepage. All right, so that's just a fact. That's how we do it. Now, again, in practice, this can't possibly work because these trees are too big, right? Their number of leaves here is all possible 32-byte strings, so that's not really practical, but we'll deal with that just in just a minute. Right, so we're going to send 1 random tree to the server and 1 random tree to the helper. The server and the helper by themselves learn nothing at all about our home pages. Okay, that's kind of how we share this data. And then we're going to do this again and again and again. Okay, so we're going to send these 2 shares, and every client is going to send these shares of the tree to each other. Okay, let's say there are M clients, so now we have M shares of the tree. Each of the servers themselves is going to add up the shares that they got. So you see, this top server basically adds up all the trees that it got from all the clients. The helper is going to add up all the trees that it got from its clients. And now comes the interesting part. Okay, so now they have a sharing of a sum of the 2 trees. These are, again, random. The top tree is just a random tree. The bottom tree is just a random tree. But the top is the sum of all the trees they got from all the clients, and the bottom is the sum of all the tree that the helper got from all the clients. So now what do? Let's say that the threshold is 3. So what they do is they start by revealing the root node. Okay, so the two helpers, the server and the helper, reveal the top. They open up the two roots of the trees and sum up the values, and so we get, you see, 9 plus minus 3. We get 6 over here. So we know that there were 6 users overall that contributed data. Okay, because that's the total number of contributions overall. The next thing they do is they open the bottom level. They open the second level. Now you see there's a 2. They open this to a 2 and this to a 4. Since the left node opens to a 2, we know that there are no leaves under this left node will exceed the threshold. So we can simply ignore all the leaves on the left and only continue down the right path. And we keep on going all the way until we actually hit a heavy leaf. And this way, only the heavy leaves are revealed. Okay, so we kind of do this repeated binary search to find leaves that are whose weight is bigger than t, and only those leaves are revealed. Yeah, so this is an easy way to reveal the heavy hitters and reveal nothing else. So that's kind of conceptually how the system works, but unfortunately, this is not really practical, right? So this is correct. The server finds all the heavy hitters and learns nothing else. If one server is honest, right, the server will learn the prefixes of all the heavy hitters. So the question is, does this work? And we already said, no, it's not enough because these trees are too big, right? Each tree contains too many nodes, and this is kind of where all the work went. Okay, so now the problem is we have these exponentially sized trees. Somehow we need to compress them into a reasonable size description, and that's really kind of where all the work was involved. So here I'm not going to go into the cryptographic details. We use something called a distributed point function, which maybe you know, maybe you don't know. It turns out even the basic concept of a distributed point function was not sufficient. We had to use something a little bit different called an incremental distributed point function. The point is we can compress all these trees so the amount of traffic that's sent to the two servers is relatively small. Okay, so that's one problem. So that makes it into a practical protocol. The second problem is that each client can actually send malformed data, right? Each client can send sort of a bogus tree and completely disrupt the entire computation. And so it turns out we can, again, using fairly simple proofs, we can actually prove that the trees were well formed, and that gives us actually a robust system that doesn't require too much communication. Okay, so the overall work for the server is just proportional to the number of clients times the length of the contributions, the length of the URLs, 32 bytes in this case, which is very, very reasonable. It's just symmetric key work, no public key operations. So this is a very practical way to get heavy hitters. All right? So how am I doing on time? Good? Okay. So actually, you know what? I think I'm going to actually skip the next one, though. And so let me see here. So so I wanted to show you basically how to recover these heavy hitters. I'll tell you, I was going to show you also how to recover histograms privately. It turns out we can recover histograms using the shuffle idea that I showed you before. And so, we kind of have a nice way to do shuffles for this exact problem, and it allows us to recover histograms. But I think in the interest of time, I will skip that. So let me just run through this very quickly. This mask is killing me, so I think I'll just skip that and jump to my summary slide. Okay, so basically, what I just showed you is kind of two ways to compute these statistics. One is for privately computing heavy hitters. Another is for computing histograms privately, histograms over a user data set. These are all kind of lightweight protocols, right? So done using secret sharing between the actual server and a helper server. And it allows you to kind of collect this aggregate information without learning anything else about the user population. So if any of these problems sort of come up in your line of work, please come see us, because these are exactly the kind of problems we like to work on. So we would be happy to help. The heavy hitter problem specifically, we started working on this because some company came to us and said, hey, this is a real problem we'd like to solve. And so that's why we started designing these protocols. Yeah. So like I said, if there are more examples like this that you see yourself, please come talk to us, and we would love to help you out and kind of design protocols to do this efficiently. Okay. So I think I will stop here and maybe get us on track. And thank you very much. Happy to take any questions. Yeah, yeah, please.
I want to make sure I understand maybe the trade-offs.
Yeah.
In approaching the solution well. Thank you. So I guess as a user maybe of the solution, I would be interested in taking such a solution to avoid all the pain and expense in securing PII that I would collect at my backend, right?
Yeah.
But in the examples that you gave, naively, right, it seems that the question is, okay, how do I separate maybe the user identity from the rest of the data? And so why would I choose such an approach, right, with its own cost over maybe severing the data collected from the user part, right, at the collection point or at collection time?
Okay, so what you're saying is, so you're saying maybe there's an alternative way to do things where everybody just sends all their data to the cloud, and then the cloud will separate PII from the data, and then the cloud will just do the aggregation by itself.
Or even I'm sending my usage data, right? But I'm not sending who I am. I'm just, hey, this random client out there saying, hey, this is my home URL, and this is my usage data.
Well, I mean, if you set your home URL to be your homepage, then sending your home URL is already quite problematic, right, in the clear, because you're actually revealing who you are. So in a lot of these cases, sending the data is already problematic, right? If you send location data very quickly reveals, if you send a few locations, that very quickly already reveals who you are. So it's a very good question, yeah? But generally, sending this data in the clear is already revealing a lot to the cloud. So you'd be trusting the cloud to only aggregate the data and throw away the specific data. What these systems let you do is basically do that without trusting the cloud. Yeah? So it reduces trust in the cloud to do things right the correct way. Yeah. Yeah. So, but it's a good question. Is that clear? Yeah. Yeah, please. Not collusion. So one of the problems is the data integrity problem. So what happens if some user tries to disrupt the computation? So they send junk to one server and they say junk to the other server, and now they kind of disrupt the entire computation by doing that. So we get around that actually by providing these very lightweight proofs that allow the two servers to, as part of computing the aggregate, they're also able to verify that what the user sent is actually correct data. So it's not going to disrupt the computation.
I meant collusion between the helper and the server.
Yeah. No, that we cannot solve. So collusion between the helper and the server has to be solved only using, basically by contracts. Yeah. So unfortunately, here we have to rely on real-world processes. Yeah. So it's kind of interesting in that because the most efficient protocols for private aggregation basically run with two non-colluding servers. In some sense, you can see the helper, all it's doing is really doing nothing. All it's doing is receiving random junk from the users, and it's just basically helping the server compute the aggregate data. It's really just there to make sure that the server learns nothing other than the aggregate data. So in some sense, I would like to encourage you, this is kind of maybe a potential business to set up, right? So a non-colluding second party, right? That could be like potentially, I don't know, maybe this is like a startup idea. Interestingly, it's a startup that can never be bought, because the minute it's bought, it's no longer a non-colluding party. Yeah, so maybe not such a great startup idea. But regardless, there is a kind of an opportunity here, or there's a need for someone to act as a non-colluding party. Right now, there is someone who's stepped up and is providing those services for certain systems, but more generally, there's kind of a general need for an entity like that. Yeah, so it's a good question, but basically, that's kind of the most efficient protocols assume non-colluding parties, and that will be enforced by real-world processes. I should say there are solutions that only require a single server, but they're much, much more heavyweight. Yeah, and so not clear that it would scale to billions of users. Yeah, it's a good question. Yeah, please. For storing what?
For learning about who is producing that aggregate data for target marketing and things like that.
So can the helper be used for learning who is producing the aggregate data?
Yeah, where is that aggregate data is coming from?
You mean who the clients are?
Yeah, at least some location about those clients. Where are most of those clients aggregated? Like maybe like a zip code or city or whatever.
I see.
Because that can be used for both targeted marketing as well as to control the hate speeches, like as the previous speaker was saying.
I see. So the two talks are connected after all. Potentially, but why don't we talk about that offline?
Okay.
Maybe there's a way, maybe there's something here.
Okay.
Yeah, it's an interesting point. Okay, terrific. So thank you very much, and let's move on.